let me start recording. Okay, here we go. Now we're recording. So yeah, so again, we're talking about vectors in the plane. A vector can be used to describe force, velocity. Those are physics quantities that you would deal with if you're going to take physics next year or doing it right now. It involves both magnitude and direction. Magnitude is kind of like length. So length of the arrows, like the magnitude, like how strong the force is, or how strong the velocity is. Direction, how the arrow is pointing, that also matters too. And there's some trig that's going to play a role with this, which we'll see. Usually we use vectors because you can't express something as a single number. So for example, like projectile motion, right? Like let's say you're launching something, a rocket or whatever, or a football or basketball. You want to be able to describe that motion in 2 dimensions, right? We would use a vector to do that because you have a horizontal component and a vertical component. So that's why, because things don't purely go horizontally or vertically, right? They have some sort of angle or direction. And of course, sometimes things go faster or slower depending on how much energy is being expended on that object. So first off, let's talk about some terms. A scalar. A scalar is just a number that doesn't involve direction. Speed, for example. Speed is a scalar. Speed doesn't involve direction at all. Speed is just simply how fast you're moving. It's actually the absolute value of velocity, if you think about it. So it doesn't involve direction at all. So it's always a positive value. But a vector is one where it has 2 things you have to consider, the magnitude and the direction. So let's look at PQ here. So how would you actually draw it? Oh, hold on, my stylus. Hold on. Here we go. Perfect. Wait. Okay, I'm gonna have to use my mouse, but I think my stylus needs a charge. Sorry, guys. I have no idea what's going on here. Okay, now I just broke my stylus. Awesome. All right. Okay, where's my mouse? Okay, so anyway, P and Q. So when you write it like this, the order does matter because see how the arrow is pointing from left to right, and P is the first letter and Q is the second letter. So we consider P to be the initial point, and we consider Q to be the terminal point where it ends. The terminal point. The length of the arrow is the magnitude. So length of arrow is the magnitude. We'll worry about direction later. Let's talk about another vector. I don't know why I wasn't in the notes, but let's see, AB. So here's yet another vector I could draw. So A is the starting point, B is the terminal point. So yeah, there you go. Do good. Because it's direction also. We haven't talked about direction yet.
But like the arrow part doesn't like add to
the just the length of the arrow. I mean, where it ends, that will play the role of magnitude. Yeah. And again, that's the length. Now, yeah, Ryan, go ahead.
When you say length of arrow is the magnitude, like do you mean like the length of P to Q?
Actually, the arrow should, yeah. So Q should have been. I don't know. I did that. Q should have been right at the arrow head. My bad. Yeah, it should have been right there. I don't know why I did that. There you go. The way you note the notation you use. So just like you see right now, PQ with an arrow or AB with an arrow. By the way, if you want to relabel them, you totally could. Like, for example, what if you want to call this just a single letter, like U or V? By the way, those are very common letters used. I don't know why, but they just are for vectors. So sometimes if you want to just like give it a single letter, just keep things simple, you can. That's totally fine. You can do that too. Yeah, totally. Yeah, if you want to, sure. You can do subscripts. Absolutely. Now, the length of the vector, the magnitude, the notation, it looks like this. It's a little confusing at first, but it's just notation we use. So you do like double lines. It looks like absolute value, but it's not absolute value. So when you see that, you see like double lines, and you see the vector inside. That's just telling you want the length of the vector or the magnitude of the vector. That's what it means. Or if I did something like this here, AB. Again, it's just the length of the vector. You can do the same thing with like U and V, same thing, you know. So just notation stuff, that's all. Okay. And now to find the magnitude, we're going to be using basically an extension of Pythagorean theorem or distance formula. We'll talk about that when we get there. And just to know, vectors have the same magnitude and the same direction are what we consider to be equivalent. So those are equivalent vectors if they're going the same direction and they have the same length. Okay, so that's just kind of the basics. Don't overthink it. Just make sure you're comfortable with notation. Questions at all? We're good? Okay. So let's move on to example one. Okay, example one. So U represents a vector, great. This is going to contain the points P and Q. V will be another vector. Will contain the points R and S. Let's draw them. Okay, it's not that hard, guys. It's actually really, really easy. Just plot U 0, 0, plot 3, 1, and draw an arrow. That's it. That's PQ. Let me change colors for the other vector. So you draw a point at 2, 2, draw a point at 5, 3, and connect them. That's it. Okay. So I'll call this V. And we put the little arrow that's indicating you're dealing with a vector. And the other one, I'll call it U. There we go. Now, notice that initial point of view is at the origin, and the x and y values, the terminal point are q equals 3, 1, describe the horizontal and vertical directed amounts that you would need to go. Yeah, so what's happening for you, think of it like this. It's like ride or run in a way. Like, how far does this run? How far does this go up? Yeah, this rise goes up 1, right? This one actually does the same thing, right? And did it look parallel to you? These are equivalent vectors, by the way. So these right here happen to be, and I'll go over more detail in just a little bit. Just hold on to any questions you might have for now. But those are equivalent vectors, mainly because they have the same length. And the same direction.
So where it is doesn't matter.
Nope, doesn't matter. Won't matter at all. This leads me to the next point about component form. Component form is, it's kind of like a pair of coordinates. I'll put in quotations because it's not really coordinates, but it's kind of like it. So notice how I put 3, 1, 3, 1. So for vector U, we could write it like that. For vector D, I've also write it. What this means is that this is the horizontal component, and that's a vertical component. Let me explain what that means in the physics relationship. Say you launch something, right? And say it goes up 1 foot in the air, travels 3 feet. That's exactly what this means. So it's kind of like if you were to launch something, it travels 3 feet horizontally and 1 foot horizontally. I'm sorry, 1 foot vertically. So that's what it means. Same thing, it travels 3 feet horizontally, 1 foot vertically. So we call these component form. The first one's horizontal, second vertical. So it's kind of like a pair of coordinates, kind of X, Y a little bit. Sometimes some people like to do this. You might see this later on, especially in college, where you can see the advanced sockets for sockets here. Some people use like letters I and J. I is the horizontal component, J is the vertical component, and the coefficient just tells you how far you move in that direction. Of course, J has a coefficient of 1, so it's 1 going up 1. So we sometimes denote it with like these, it's not parentheses, it's not brackets. It kind of looks like these inequality signs in a way. It's kind of weird. But that's how you break down the vector into its components, into horizontal vertical components. When you create these vectors, just so you know, so even though this starts at a different place than this one did, when you create the vector is actually created like this. That's how you create the vector. You simply subtract the x's and subtract the y's, as I just did over here, right? Subtract the x's, which is 3, subtract the y's 1, same here, 3 and 1. So that's really what you're doing is you're taking the final point minus the initial point for each point. Everything I probably just described might be on the next page. I haven't checked the notes yet, so I might be getting a little ahead of myself, but that's how you write a vector. That's how you express it. That's what's going on with the components. Once we start doing some computations, it'll start sinking and making more sense. Questions so far? No? Okay. And vectors, to be honest, a lot of it was created to help make physics easier to understand, especially when you're doing 2 dimensions, right? So let's go on to the next page. So are they equivalent? Of course, absolutely. So yes, they are. 2 ways to show they are equivalent. One way is you can, let me actually do a text box here. Show that each vector has the same length and direction. Not too hard. Or another way, find the component form of U and V and see if they're the same. And the component form, remember, is x2 minus x1, comma, y2 minus y1. Hold on. Well, sorry, was the question? Go ahead. Totally, 100% can. Yep. Because so far, the vectors that do are going to the right, we can go to the left. If we go to the left, that's in that direction, 100%. Totally. Yeah, so I kind of already described it here. To find the component form, you have P1, P2, Q1. I use X1, Y1, whatever, it's all the same. But yeah, it's just simply subtracting those with each other. So kind of weird how they did it. I don't know why it's written that way, but Q1 minus P1, comma Q2 minus P2. Basically the change in X and change in Y. There you go. So again, you guys are getting all the vector basics, all the vector fundamentals. And to show their component forms, I kind of already did it, but I'll do it again. So U is going to be 3 minus 0, comma 1 minus 0, which of course is 3, comma 1. And V, I'll do up here because I'm running out of space. 5 minus 2, 3 minus 2, 3, comma 1. Okay, we're cool. Let's just go down there. Questions? No, we're okay. All right, let's keep on moving. So magnitude of U. Again, we write like this. So it kind of looks like a V. My apologies. It's all it really is just this. The square root of U1 squared plus U2 squared. So, for example, we have this, right? Well, U. And what was the vector? How's it labeled? Is it V1, right? So all you do is we do 3 squared plus 1 squared, which is root 10. Where's that come from? this formula. It's what Pythagoras did, yeah. It's just basically, oh yeah, let's do it around time with it, right? 3 and 1. That's what they are, right? Just Pythag. Now, a unit vector is a vector with magnitude of 1. And a zero vector is magnitude of 0, which means it's just a point. Because there's no length to it, obviously, right? But a unit vector has a length of 1. There's a reason why we care about unit vectors. They actually do play a very significant role in vectors. We'll cross that bridge when we get there. But that's what a unit vector is, magnitude of 1. So questions so far? All right. So again, it should be very basic. So let's look at example 2 now. For example 2, very simple. You're just going to plot the point. So 4, -7. So 4, -7. Oh goodness, I'm going to have to look this closely. 1, 2, 3, 4. Okay. 1, 1, 5. 1, 2, 3, 4, 5. And you want to go in this direction, right? Oh, look, that was quite straight for freehand. I'm actually quite impressed with myself. It is very impressive. Yeah. All right. Just like the Mavs being the crap out of the Eagles. It was very impressive. All right. Yeah, exactly. At 30-20, but I'll take 42-19. All right. So you have to find the excuse me, find the component form. Easy. -1 minus 4. So you do final minus initial, guys. Always final minus initial. So again, it's always going to be final minus initial. Okay? Final minus initial. So you get -5, 12. Right? -5, 12. The magnitude. And we're calling this V. So I'll do the little symbol there. Simply just -5 squared plus 12 squared. What's that, guys? Excellent. You know your Pythagorean triples. Very good. And that's vector V right there. So again, really easy. When you guys do about AP Calculus BC next year, you will do some calculus called vectors. So you guys will probably forget this because you probably guys won't do this till about a year from now or so. I mean, I'm sure you'll review it, whoever teaches AP Calculus BC, but at least I'm introducing it to you guys. And this will get reinforced, by the way, in physics big times, because I think most of you guys do AP Physics. So a lot of this does get reinforced in physics. Okay, we're good? All right, let's keep moving. Easy peasy. All right. Vector operations. This is the part that's more fun. Okay. So you can scale up vectors or scale them down. Up to you. So K is what we call a scalar. So it's like a coefficient. It's actually distributive, believe it or not. It is distributive. That's what's happening. So if I put K on the outside, and here I got V1, comma V2, then guess what? It's just KV1, comma KV2. So say, for example, that was V1, that was V2. And then say I double them up. So that's 2V1. That's 2V2. So that's all that's just happening. You're just scaling them up. Or what if you did half? Hold on. Yeah, so that's all. By the way, the true vectors are going to be this. The true vectors was these in black. What more of these here do you want to do? Those are the components, right? V1 is the horizontal component, V2 is the vertical component. And that's V. But if I decide to double V, then what if I actually double the components, right? Which would make, if we double the legs or a triangle, how the hypotenuse is a double? Yeah, because similar triangles. These are similar triangles. Or what if I take half of V here, half of the sector? Guess what? The components also go down, right? So yeah, so it's just a scale. That's all it is. By the way, K can be negative also. Now reverse the direction. We'll talk about that too. But it could be negative. Okay, vector addition, really, really, really easy. You just add the components. That's all you do. So here you just do U1 plus V1 or U2 plus V2. That's it. If you make a negative, make a negative. If you subtract, subtract. So it'd be U1 minus V1, U2 minus V2. Now, subtracting is going to be a little funny. The way you want to think of this is U plus the negative of V. Because the negative means you change direction. Or let me rephrase that. Opposite direction. So say, for example, driving from, let's say you live in Redwood City, driving towards Sacred Heart. That's the positive direction. You realize you forgot something at home. Say you're on I don't know, where the Jack in the Box is, or Chavez Meat Market. I love the burritos there. You turn around. Chavez is the best carne asada burritos in town, I think.
That's true. That's true.
They're incredible. Yeah, I it's my guilty pleasure. Anyway.
I give Chavez burritos at the volleyball.
Every week.
Like,
All right, there you go. All right. Anyway, but when you're subtracting vectors, think of it this way. It's like you take the vector you're subtracting by, and you're doing the opposite direction, and it's plus the negative counterpart. That's the best way to think of vector subtraction. So let's actually do the drawings down below, because that's going to be a part that you really need to understand how to visualize it. Very, very important that you visualize it correctly. Here we go. So what if vector U was this? Let's color code here. This part that I had to kind of slow down a little bit because I don't want you guys getting lost. Okay, I'm just totally making this up. I don't know where U is exactly, but let's say this is U. And say this is V. Hold on. Okay, so let's say V is somewhere over there and U is over there. If you wanted to add these, what you do is you take one of these vectors and you connect them head to tail. Very, very important. You connect them head to tail. To add vectors, connect the head of one vector to the tail of the other vector. Yeah. What's that? Probably another half hour. Yeah. Yeah. So that's what you do. So what I'm going to take V and do that. All of these I translated it.
Did you have added to?
Oh, I know.
Totally, 100% you could have, yeah. Yeah, just translate one of the vectors. Don't dilate because you change the magnitude, and don't rotate and change the direction. You simply just translate. Simply just take it and just shift it that way, or shift it up or down, whatever.
So like, because you need to have like a direction as vectors, like, how do you say is the direction?
I'm gonna get there. Okay. Okay. So when you add the vectors, it looks like this, guys. So that right there is considered u plus v. Great example would be if you're looking at an airplane and wind speed, or a boat in the direction of the currents. For example, if the airplane is pointing a certain direction and the wind's going a certain direction, guess what? The combination of that would be something like this. So say you're taking off from SFO, the wind's blowing that way, that's the plane going to be directed. Or say you're like on a river and you're going, or the bay, the ocean, and you're going this way and the current's going in a certain direction, then that's going to be the overall direction of the boat, right? Or say, for example, you're playing golf. That's a great example. Anyone play golf in the spring for the sake of heart? That's a great example because the wind can impact the direction of your ball many times, right? Depending on the strength of the wind and direction of the wind. So you could be like how you the launch angle, how you launch the ball, then V could be the wind, how the wind's moving the ball, right? So that's what you do. That's how you add vectors. Now, if you want to subtract vectors, here's what you do. I'm just gonna again totally make this up. Let's say U is right here. Let me go kind of let me just try. I'll say this is U, and say this is V. Okay. So what you're gonna do if you're doing U minus V, so you want to do vector U minus vector V. Think of it like this: vector U plus the negative of vector V. So what's the negative vector V going to look like? It's going to be reversed, clearly. Right? I just took vector V, just rotate 180 degrees, right? So going that way, it's going that. Now I'm just going to take this guy and translate it so that head of this connects to tail of this, or the other way around. The tail of this connects to the sorry, head of this connects to this. It's up to you. But I'm going to take this guy. Actually, and this is the cool thing. I think I could actually hold on. Let me move that down here. This is the cool thing to zoom. Negative V. Let's try this here. Yeah, I'm gonna take this and see. Look at that. That's cool. I like that. Okay. A little distracting, that extra negative V thing there. Probably should have got rid of it. Just gotta use steady hands. All right, and then that right there. Again, this is negative V. That right there is that's messy, sorry. Vector U minus vector V. That in black. So we still connect head and tail, but treat it like addition. Treat it like addition. So if you're doing U minus V, think of what V is, reverse it, and then connect head to tail. And the connection between the tail of the first and the head of the second is the final vector. So I didn't make that clear actually. So we call this the resultant vector. That's another word that's used sometimes. I don't know if that's in the notes, but it's what results. It's called the resultant vector. And the way you draw that is you connect tail of the first vector with the head of the second vector. So, That's a resultant vector. Question, Brian, go ahead.
Does the V, does like the arrow on the V still point the same way if you flip it and spacing it?
Oh, yeah. Oh, you mean this little arrow here?
Yeah.
That doesn't matter. It's a symbol. Okay. Yeah, don't worry about that. All right, good.
Is the resultant vector always gonna point in the direction that the triangle opened?
Yeah, yes, right, exactly. Yes. Payne, go ahead.
So it's the scale of. So
That's the result. Now, when you connect them, you connect the head of one to the tail of the other, right? And you can do it. I did that the other way. I've done it. But when you finally close it down, right. When you close it down, exactly. Just think about it. What if you let's say you're on the boat, and say you're paddling this direction, and the current, you're going against the current, right? And that current's really strong. Guess what? You're going backwards, right? If you can't swim fast or row fast enough to that current, that's take me down the other way, down the water when you're done. So, you're in Yosemite, so I'm just kidding. So, yeah, by the way, if you're ever in Yosemite, be very careful. So, anyway. All right, let's keep moving, guys. Okay. So -1, 3 is right here. Okay. And let's go green for the other one. 4, 7. Oh goodness. 4, 1, 2, 3, 4, 5, 6, 7. Okay, so we got vector V. We got vector U. Okay. So how would you actually connect this? So you could actually wind up doing something like this here. You could take vector V. You kind of do that, right? And then I'll just draw. So it'll look kind of like that.
Does the order matter? If
No.
You're starting at the origin.
Nope, doesn't matter. So when you do U plus V, it's simple. It's -1 plus 4, comma 3 plus 7, or 3 comma 10. Guess what? If I look at what I drew in black, count 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It makes sense, right? So that totally could work. So what I should have done when I drew, let me back up a little bit because this might be a little confusing. But what I probably should have done was this. When I initially drew it, let me draw 4, 7, just kind of like that, right? That's V. Yeah, and then what I do from here, from the head of the first vector, go 1 left, 3 up. That's what I should have done initially. So my bad, I didn't do that initially. But go 1 left, 3 up. And then you just, yeah. So you do that. Or if you start with U. I could have done this, guys. I could have started here. And then gone 4 right, 1, 2, 3, 4, 7. It'll still be the same thing. It's still going 3 right, 10 up, still the same thing. Okay. Well, Audie, let me give you the notes. Hold on. And I'm recording, so don't worry. That's fine. Yeah, because you're gonna go online. Right? I'll put notes in a little bit. Okay. Actually, let me pause this for a sec. Let me email these notes, Audie. Hold on. All right, back to recording again. All right. So let's look at B. You got 3U. And look at my pacing too. Maybe we can get. We'll see. We'll see. Maybe we can get this done before 3:15. It's a lot. I know it's a lot, guys. Thank you for your patience. Okay, here we go. So 3u. Remember, u is this. U is that. Remember, what was u again? It was -1, 3. So what's 3u going to be? Yeah, so you got to triple that size. So you could think of it like this. 1 left, 3 up. One left, 3 up.
You have to do 3 arrows.
No, you just draw 1 arrow. I'm just showing you what happens. That's all. Ultimately, it's basically just this, right? That's all it is. It's like that. By the way, the starting point of the vector is completely irrelevant. Starting point could be whatever. So just so you know, when drawing vectors, yeah, it's completely irrelevant. So don't worry about it. All right, let's do one more here and let's look at part C. Okay. And we'll talk about direction.
If you know what the resultant vector is, you're solving it like different components. You have to draw the whole triangle.
No, just a yeah, which we're gonna talk about that actually near the end of the notes. Okay. So 2u, guys, quiet please. Thank you. So u is -1, 3. So you're gonna have 2. 2 -1, 3 plus, and if you reverse v, reverse means you change the sign of it. That's all. So it'll be -4, -7. So overall, it's going to be -2, 6 plus -4, -7. Or it's going to be -6, -1. So you don't really have to draw the at this point, like to Brooke's point, like, yeah, just draw it. Just draw what results afterwards. 1, 2, 3, 4, 5, 6. Yeah, that's good enough. That works for me, guys. No, you don't have to. Well, once you kind of just know like how to combine it, how using basic arithmetic, just draw what results. There you go. You don't. I just want to show the geometry of it, but I think I already kind of made that point. So yeah, you could just draw what results and move on. Okay. Let's keep on trucking here. Unit vectors, direction, angles, and application. Okay. So we already talked about what a unit vector is. It has a magnitude of 1, right? Unit vector has a magnitude of 1. So what you do, you just reduce it. You guys remember when you guys did trig, like, say for example, you have the point 4, 3. Don't write this down, by the way. You have the point 4, 3. Remember you had to draw an angle kind of like this? And you had to like find like the sine, cosine, tangent of it. But the radius, sorry, the hypotenuse is not 1. The hypotenuse is like 5. And how did you find sine, cosine, tangent? You did like x over r was like cosine, right? Cosine theta, that's theta, was x over r, or sine theta was y over r, right? So that's kind of what's happening here. Is that the hypotenuse, like the vector is not like the 1, so you want to reduce it, or it maybe it's really tiny and you want to make it bigger. Here's what you do. To find the unit vector, you simply take the vector itself and you divide by the magnitude. You take the vector itself and divide by the magnitude. So essentially the unit vector would look like kind of like this. where this would have a length of 1. And these can exactly 100%. Yes, that's all we care about. Maintain the direction, but the length will change. So you can think of like this: V1 over the magnitude, and V2 over the magnitude. Where this would be like right here, and this would be like right there. That's what's going on with the unit vector. So we asked in example 4 to find the unit vector. All you have to do, question, are you good? No, I thought you had a question, are you? No, sorry. Yeah, so all you have to do for example 4 is this. Find the magnitude. That's not hard. That's root 29. Just gonna kind of just get straight to it. So the unit vector is simply going to be -2 over root 29, comma 5 over root 29. That's all. Yep. And the magnitude would be 1 if you actually were to compute that. If you were to actually, do like this, don't write this down, by the way. But if you were to actually work that out, what would this come out to being, guys? If you work this out, 4 over 29 is 25. That's 29. So you kind of force an issue to make the length 1. And if you were to draw it, so that's V.
Actually, it's not covered.
That'd be the unit vector. Yeah. Okay. Let's keep moving, guys. Okay. So, and I think what I might do, I might skip down to the last example in just a sec, but let me finish this, writing this right here. So the unit vector is 1, 0. And 0, 1. You can rewrite them as actually, hold on, I'm not sure what's going on. Let's just skip this part for now. This part seems confusing. Sorry. Let's just go straight to example 10, guys. My apologies. Here, I care more about this. And then we'll stop there after this. Okay, here we go. Okay, so this is because I've been talking about why we do this, how it plays well in physics. I feel bad if I didn't get to this part. I feel like this ties together really nicely. All the stuff in the middle, we can finish off on Wednesday. 5 miles per hour, bearing, no, bearing. So bearing is when you start with the north direction. You go walking. Sorry, so like pointing north, you're going in this direction here. So I'll show you. And fixed altitude with actual wind velocity, but then it encounters a wind. And wind blows in that direction, that magnitude. What is the resultant speed and direction of the airplane around the 3 decimal places? Okay, so here's what we're gonna do. So we'll do the airplane in red. This is basically in still air. If we're in still air, it will look like this. So 330. So bearing does this. You rotate until you hit 330. Tell me when you think I should stop. Perfect, good. Okay, so that's the airplane. I'm gonna erase the other stuff just so it's not confusing. Okay. Oh, thanks. And here are the notes. Okay. Okay, wind. Wind has now when it says direction angle. Actually, no, we're fine. We do the same thing. Okay, so wind I'll do in green. And it's shorter. And 45 degrees means this, right? That's 45 degrees. So we have 45 degrees that way. Okay. So when I combine it, let me take this part right here.
Otherwise, how you find like your separate. No.
So this is truly what the airplane's seeing, right? Because remember, the airplane's going this way somewhere. The wind kind of pushes it a little bit. Of course, airplanes try to make adjustments to get to where they want to, but we won't worry about that. Very, very simple. Here's what you do, guys. You write each vector like this. You take the velocity times cosine theta, velocity times sine theta. That's what you do. So you're going to break it down to their components. So we'll do it for the airplane. And we'll do it for the wind. What's the velocity of the airplane again? 500 times cosine. Now careful with this one. You can say cosine of what, guys? Careful here. Good, 120, yes. And 500 times sine 120. Because that's truly 120 degrees, like right there, right? And the wind, you're going to do 70 times cosine 45 degrees and 70 times sine 45 degrees. It's something called bearing Audi. I'll have to explain that. Is that what you're asking about, or?
Oh, no, I was.
Okay.
Yeah.
Okay. So if I do, okay, since everyone's here, I'll just do on the board. So airplane will be 500 times negative half. 500 times root 3 over 2. Wind will be 500 times root 2 over 2. And 500 times root 2 over 2. Oh, yep, sorry. You're right. I'm going to start using decimals because that's I have no choice but to do that eventually. If I were to put that in decimals, I should get, okay, that's negative 250. And 500 times root 3 divided by 2. That's 433.013. I go 3 decimal places. Root 2. 2 times 70. 49.497. 49.497. And guess what? We're going to add these together. We're going to add these together. So negative 200.503. 482.510. So that's the final vector, which makes sense because it is going to 11, it's pointing up by quite a bit. So now, the speed will be the magnitude. And the direction, this is the part that should be 2 hopefully. Tangent theta equals y over x. You think like that. Think it's tangent theta is y over x. In this case, you're just doing basically root x squared plus y squared, or root negative 200.503 squared plus 482.510 squared. Looking at time should be 7. And then here, beta will be the inverse tan of 482.510 or negative 200.503. So that one should be pretty easy. If I square that, add to the square. Of that, root it. You should get 522.511 miles per hour. And then here, I do 482.510 divided by negative 200.503. Inverse tan it. So you get, gotta switch to degrees. Wait, so that number wrong. Hold on, guys, sorry. You should get negative 6.7. But does that make sense, guys? Nice 6.7? No, right? You gotta make an adjustment and add 180 to it.
Wait, why are you?
Because add 180 to it, and we'll keep working on this throughout the week.
We always do the same thing.
Yeah.
This is our third. And next,
Good question that Duke asked. Yeah, if you want to convert back the bearings, I'm not gonna do that today because bell's gonna ring in a minute and a half. But at least we kind of know generally the angle. Personally, bearing is a little confusing. So I think what I'm gonna do on the final exam, I won't use bearings, you guys. I'll just say use the angle like you would in a unit, right? Just start with positive x-axis and the positive x is going counterclockwise. So we'll say that angle of that airplane is actually 112, whereas it's still there at 120, and the wind was. Yo, what's up there for today? Homework, let me hand out to you guys.
so magnitude.
Okay, here's the homework packet. It's also I'll tell you which ones to do in school. So I'll try to schools in next week.
So magnitude is the length of the vector. But in this instance, we don't say magnitude is distance. Magnitude is never the same. But it's the length of the vector. So the vector doesn't actually represent this.
You just use the length to say like this vector has a larger magnitude. So that's like the point is off. It's not just.
I'm gonna let that. I'm gonna sit on that. Sit on it. But you're so fucked up. I like you barely. You have an ear infection? I don't know. Remember that sound effect of I knock on it. It was as bad as you could see. I mean, not lucky in his point.
Wait, you went to Arizona?
You
have any discussion?
Oh,
beers?
Like,
No, it was good. It's only good.
I didn't think you know. This is like basic level grade. Different thing. Just went off the rails. This is like whatever, 47 minutes.
It was like an hour.
We talked about it for literally 3 minutes. And then we moved on to the. Yeah, nobody could figure out how to open it. I know, it's fact that we had the conversation about how to open it and then they speak.
All right, thank you, Mr. Reed.
Later.
Thank you.
Oh.
See you guys.
You photos you got on your desk there.
Well, thank you, appreciate it, yeah. I got for my birthday, I figured I should put it up, so.
Nice. Nice put them.
Exactly.
Showing, like teaching, like
Right.
proctoring.